Okay, so one of the things that I've been sent recently is a Cleartone CM9000, which needed some repairs doing to it, and amongst the bundle was a Tigertronics Signalink. I did the repairs on the radio, but the interface didn't want to play ball. I've done some tests on the interface itself, and the actual USB audio codec chip itself is dead. So I've bought a new chip for it, and we're going to attempt to unsolder the old one and solder a new one onto the Signalink here. Let's see how it goes.
A few moments later.
Okay, so what I'll do now is take you through this Signalink board. I'll just point out a few bits and bobs on here. So you've got the main USB B-type header at the top here, and obviously the computer, the only thing that the computer is seeing is this chip here. It's a Texas Instruments part, and it's the USB audio sound card, basically. So when you get these cheap Chinese USB sound cards from eBay, often they'll have a chip like this inside them, and the chip's very simple, it's quite easy to implement, it's quite a good chip, they're still in manufacture, and the chip's got a few legs that go straight to the pins on the USB connector, and inside the chip it handles everything that's USB related. It's got a few analog inputs and a few analog outputs. So the analog inputs are the essentially left and right microphone, and the analog outputs are the left and right speaker. So the audio actually passes through a couple of op amps. There's one here and one there. Operational amplifiers, they're just taking the voltage level and turning it up ever so slightly, depending on what you do with the signal level on the potentiometers there. So this one here is for TX audio, which is the audio that you'll transmit. This one here is for the receive audio, in other words, the audio that your radio is receiving. So that would be your handheld audio, I guess, depending on how you're using this. If this is being used for data modes and all that sort of goodness, then it's a slightly different concept. You've got these two jumpers here. These two jumpers simply short out one of these tiny little resistors down here, and those resistors are in the signal chain. So your actual audio that comes from the sound card, which is audio from the internet, that will pass through one of these resistors down here and through a potentiometer, and also audio coming back the other way, which is through this connector here, the RJ45 connector. From your radio, that audio will come through and will pass through one of these resistors. These jumpers simply short those resistors out, which increases the signal level that's fed to the op amps there, which is why you'll get slightly louder audio. It may or may not be desirable. In an effort to try and disconnect the computer from your radio, what they've got is your audio passes through a couple of transformers of questionable heritage, let's put it that way, and it also passes through two fairly monstrous capacitors here. Presumably they're using those for DC blocking. Frankly, I wouldn't want them to start playing around with RC networks. You know, if there's something needs doing with your audio, then you'd do it externally. I wouldn't want this to be, you know, adjusting bass and treble responses and stuff. And then for the press to talk, there's the relay here. Now you've got a little PIC programmable chip here. It's a microcontroller, and what that does is it's watching the audio from the sound card, in other words the audio from the internet, on an analog input, and it's simply comparing that audio against a voltage divider. That voltage divider is set up with a couple of resistors, and one of those resistors you can short out using this jumper here, which increases the sensitivity of the Vox. There's a few. There's a lot of passives on here. These are all just termination points and to assert line levels on the sound card there. So they're either pulling a line high or pulling a line low. Lots of decoupling caps, so just DC decoupling caps. Obviously you've got the main power switch, a couple of status LEDs. There's not a lot else in this. There's the delay potentiometer that goes back to the PIC also to set how long it will keep the relay tripped to keep the radio in transmit. There's obviously, you've got your auxiliary line in and line out sockets on the back here. Now the only problem with these is that plugging something into those will affect. They're not separate. They share the same signal level as the transformers, and they share the same signal line. And so as a result, if you add any load onto these connectors by plugging a speaker in or headphones or anything else like that, if it's a fairly low impedance load, it's going to drag the signal level down, and it will affect what's going on with your radio. Which is a shame, actually. They've missed a trick there. It's a shame they didn't have them on separate amplified lines, and it's especially a shame because this is a stereo chip. It's got two audio outputs and two audio inputs, so it wouldn't have been that difficult to do that. This is a jumper section. It's just a dual inline package with sort of 8 pins in a row this side, 8 pins in a row the other side, and what you do is you connect. They correspond to the pins on your Cat 6, Cat 5 cable, whatever it is you plug into the front here. Cat 5 would be perfectly fine. It's not faster than that. And yeah, you've got your jumpers here to connect. If you've got a funky cable where speaker levels, your speaker from your radio normally say comes in on pin 1 here, say you've got a funky cable and it actually puts it in on pin 2, you can make an adjustment here on the jumpers rather than having to slice your cable apart and make changes there. I'm not sold on this. I don't know why they don't just have specific cables for specific radios, but it's there if you need it anyway. Okay, and that's about it really. So what I'm going to do now is I'm going to zoom in to this, because this is what we're going to remove now, and hopefully we're going to replace it with this, and hopefully it's going to burst into life and everything's going to be just great. Cross your fingers, eh?
2 hours later.
The next thing I'm going to do is I'm just going to cover some of the surrounding components here. With a spot of Captain tape. Oh lordy.
A few inches later.
Okay, if you guys want slick editing and Mantis microscopes, you're better off going and looking for Lewis Rossman. He's the expert at this stuff. I'm just a guy who messes around in his spare bedroom, I'm afraid.
6.5 hours later.
I'm going to put some flux onto the pins of the board. I've got it here in like a tin. It's like a tin like shoe polish. This stuff's quite gloopy, which is actually good. So I'm going to fire up the hot air gun here. and I'm just going to apply some heat to the board. I'm just scooting some underneath the board here as well. And I'm just trying to warm the temperature up on the board so that it doesn't act like such a heat sink. And my hot air gun's set to 350 degrees centigrade. If I blow the hot air gun here at the captain tape, you can see that, you know, that's not touching that captain tape at all. Meanwhile, if I do the same thing with the end of my plastic spatula here, oh dear, my plastic spatula's not doing so well now, is it? That's come off second best. So that's what captain tape does for you. It just protects things from heat a little bit. It's non-conductive, it's anti-static, or at least the half decent stuff should be, right? Okay, so everything down there is fairly well heated up. And I'm just glooping this stuff in here. Okay. That's that sorted for the flux. Now I'm going to start to apply some fairly serious heat to the chip. And I'm just ready here with my tweezers for when that solder starts to melt. Goodbye, little chip. Okay. So, that's the old chip off the board. The next detail here is going to be I want to get this old solder off the board, so all this old captain tape can go. And another liberal dose of flux. As you heat this stuff up, it does become dead flux, if you like. It's heat activated, and once it's sort of been heated up and used, that's it, it's dead. So it pays just to start with some fresh stuff there. Okay, so I'm just going to take some solder wick here. Okay. And I've just made a little shoe type shape so that I can reach over these capacitors from the left hand side. Well, I suppose it'll be the top for your perspective. Okay, that's the old solder gone. Excellent. So I'm going to take a cotton wool bud. I use acetone, which works for me. But you can see it picks up all the old flux there. But yeah, just a cotton wool bud soaked in acetone.
A little longer than a few minutes later.
The next step is I need to get some flux back on this board, and just in an effort to make it a little bit easier to work with, I'm just going to apply some more general heat to the whole board. I'm going to plonk our new chip down on here. Oh, I'm trying to reach my tub of bits and bobs. Right, because there's flux on the board, it doesn't matter if I apply some solder to the soldering iron first. And normally what you're supposed to do is only apply the solder whilst you're doing the soldering. And normally, depending on what you're doing, you'd apply the solder to the joint, not really to the soldering iron itself. However, that is not going to be a possibility here because I need 3 hands to do this. Oh, oh dear, oh dear me. Okay, and what I've done there is created a huge solder bridge, which is perfectly fine because I'm not trying to solder this chip down at this stage. I'm just trying to hold it steady. Okay, again, I'm not bothered about silly big solder bridges at this stage, I just want it held steady. Okay, that is now not going anywhere at all. So now what I can do is I can go back in there and clean that up. It's not a problem. But first I'm going to apply so much flux that it creates a choking cancerous cloud that any serious pipe smoker would be proud of. There we go. Lovely stuff. Right. Let's get cracking with the knackered pet. Okay. Flux. It's all good. So I'm going to pick out the worst of this nasty stuff with the solder braid here. Okay. The next thing is, we need to plug this in to the computer and we'll see if it fires up. Bring you back in a second. Right, so we've got the Signalink here and we're going to plug it in and we'll see if... Oh! It's a bit slow. Not the fastest machine in the world. Okay, well, I mean, the short to ground can't be that lower resistance, right? It's powered up, so that's good in the first instance. So what you're looking at here is, I'm running a program called Audacity, and I've used Audacity to generate a 1 kilohertz sine wave, and it's on for 2.5 seconds, off for 2.5 seconds. So I've got this as an audio track that I can play, and what I'm going to do is I'm going to send it to what will appear here as a USB audio codec. In other words, it's the little chip on the Signalink that it's seeing. Okay, so if I play this track, what should happen is, if this is getting the audio, it should see the audio and trip the relay, and you'll see that on the, you'll probably hear a little click and the red LED will illuminate. Okay, so it's playing and it's off. Oh, I get it, yeah, it's because we've got a load of other stuff selected here. Okay, so there we go, and it's off, and then on, and then off, and then on. Okay, so that seems convincing enough. So on the oscilloscope I've got it set up for single shot mode, so we'll see if we can pick up the audio from the test points on the board itself here. There we go. Excellent. So Okay, great. We're showing 1 kilohertz exactly, which is more a test of Audacity than anything else. So that's fairly impressive, and the fact that the Signalink reproduced that exactly, spot on, and you know, it's outputting 1.8 volts, nearly 1.9 volt peak to peak audio signal. So that's fairly strong, you know, for our needs. Okay, so now we want to go the other way. We want to put audio into the Signalink. So what I'm going to use is my signal generator. A signal generator is basically a Walkman that plays sounds and stuff. That's as technical as we need to get for what we're doing. And rather than random sounds such as music, music is quite diverse in the amount of different frequencies it plays, and it can be confusing. A signal generator like this allows me to play one frequency only. I can play, there's all sorts of stuff that it'll do, but one of the things that I can do is play one frequency very specifically to a high degree of accuracy, and I can output it at a set voltage level. So in this case we're going to hit it with 1 kilohertz again, which is the same frequency we used on here, and I'm going to hit it with 300 millivolts peak to peak, which is from the bottom of the wave. If you imagine a white line through the middle here is 0 volts, it goes up 150 millivolts, it goes back down to 0, and then down 150 millivolts. If you measure from the top to the bottom, peak to peak, it will be 300 millivolts. Okay, so what I'm going to do is I'm going to set the computer to look at the microphone on here. So if we start monitoring, this that you can see flashing around here, this is what everybody complains about with the noise floor on these devices. So I'm not injecting any audio into this whatsoever, it's just making that up as it goes along. Who knew, right? Okay, so activate the output there, and that's one channel. You can see on the top right hand side there, that's the right hand channel, and that's the left hand channel. So what we can even do here is we can record that using Audacity. So this is the other channel, because it's got two, remember it's a 2-channel device. We've got left and right. Okay, I'll just stop that there. And we can play that. Oh, of course we're sending back to the Signalink there. Excellent. Bit noisy, as that's me putting the probes across. Okay, so that's good. If we select some of that audio and then analyse it, Audacity will act like a single shot spectrum analyzer, if you like. Okay, so what you can see here is 1000 hertz, in other words 1 kilohertz, is the you know, primary frequency that you'll see here, and then there's loads of harmonics. We could probably sort that ringing out if we tried hard enough, but the main frequency is at 1 kilohertz, and that was the let me see here, the left hand channel. So we'll have a look at the other one. Same deal. Excellent. Right. So, you know, it seems to be making all the right noises, doesn't it? I think the next thing would be to have a look with this device actually connected up to a radio, and we'll try passing some audio with it, but I think that's pretty much it. What I'll do now is, it's worth noting that the repair process wasn't as slick as I'd like it to be. It's not something I have a lot of practice in, and I've got some new gear here that I'm getting used to, blah 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 blah. I'll make a load of excuses, but the long and short of it is that off camera I ended up going back in there with the hot air gun to ever so slightly reposition the chip, because it was slightly offset. I would probably have gotten away with it, but I didn't want to leave it the way that it was. It's not my device, so I thought I'd, you know, try and clean that up a little bit. So I'll include some photographs here of some close-ups, as good as I can generate with this camera, and I'll show you what sort of a finish I was able to achieve here. I've removed all the flux. I don't have a, you know, ultrasonic cleaner. This isn't, you know, iPad rehab. You know, my resources are limited here, so I've done the best I can. Anyway, I think that's it. I'll probably be doing some more videos on the CM9000 soon, connected up to this device, because it all came as one job lot from somebody, so it'd be nice to see it all working together. Okay, thanks for watching. Catch you next time.